Hello everyone, welcome to my class lecture number 4 of the first week. In this lecture we will explore algebra of limits and we will prove analytically algebra of limits of sequences. There are 4 theorems which are going to prove. So with the 2 or 3 previous slides or lectures, we have already seen that limit of a sequence is nothing but it is a real number L for which for every epsilon greater than 0 there exists a natural number M such that n minus L is less than n minus L is less than epsilon for n is greater than or equal to M, and it is written as limit n tends to equal to n tends to infinity n equal to L, or limit n equal to L, or n tends to L. Now we have already defined all these, that one sequence 1 by n is going to be 0 for which if I take M as a natural number such that M is greater than 1 by epsilon, right? So you give me any epsilon, so let's say epsilon equal to 0.5. I will choose, I will find out M equal to what? M equal to 1 divided by 0.5. So this is equal to 10 divided by 5. This is equal to how much? 2. So after the second term, it will going to be, it will fulfill these terms. So each term of after 2 n minus L is going to be less than epsilon. So that's why this is quite important. Now for two sequences, we can define sum, difference, product and quotient of the sequence term by term. So if an and bn be two sequences, then we define term wise sum. So the term wise sum, that means the sum of the two sequences a and bn is term wise a1 b1, a1 plus b1, a2 plus b2, a3 plus b3 and so on. Now you can see the sequence has the term as the sum of the two terms an and bn. Similarly, term-wise differences, each term become a difference of the term a1 minus b1, a2 minus b2, a3 minus b3 and so on. Term-wise product is also defined in the same way. So you will take one term a1, b1, second term a2, b2 and so on. Term-wise division is also the same thing, a1 by b1, a2 by b2 and a3 by b3. But remember this one, no bn is going to be 0. For each n, bn is denominator must be non-zero. There are 4 famous theorem for this limit of sequences. We call it algebra of limit of sequences, and we are going to prove each one individually. So if n and bn be two sequences such that both are the convergent sequences and converges, n converges to a here and bn converges to b, then we have to prove limit n tends to infinity n plus bn is going to be individually sum of the individual limits, and that is nothing but sum of the limiting points a plus b. Similarly, the difference between the two sequences limit n tends to infinity n minus bn is the difference between the two limiting points a minus b. Similarly, product, the limit of n tends to infinity product of the two sequences is the product of the limiting values of the two sequences a and b. Similarly, the quotient n by bn is nothing but a by b, but remember this one, denominator must be non-zero. So here b is not equal to 0 and each bn is not going to be 0. So now come to this theorem and come to the proof of that theorem. How I can prove this theorem? So for this, remember this one, every theorem and the proof of that theorem based on the definition of limit of a sequence. So if you remember the definition of the limit of a sequence, you can prove easily. There is no need to mug up. So using the definition of limit of sequences, so already here it's given, right? an and bn are two sequences such that limit of an is a and limit of bn is b. So I can use the definition of limit of sequences. So for n, let's say m1 is a natural number, see here, such that for n is greater than m1, an minus a is less than epsilon by 2. This is the definition of limiting an is equal to a, right? Similarly, for sequence bn, we have limit bn equal to b. Therefore, there exists m2. M2 is nothing but M2 is a natural number such that Bn minus B modulus is less than epsilon by 2. Now take these two maximum of these two natural numbers M1 and M2 and name it as M. Then An minus A is less than epsilon by 2 for now replacing M1 by M, and here also replacing M2 by M. So An minus A is less than epsilon by 2 and Bn minus B is less than epsilon by 2 for the same for each n is greater than or equal to M. Therefore, I can calculate A and Bn, the sequence minus their limiting values, right? I mean, if you remember this one, for this we have calculated this one. This is the same thing. I am going to prove that this is the limit value of this sequence, right? So, An plus Bn minus A plus B, I am going to calculate modulus of that, I am going to calculate it. So, this can be written as An minus A plus Bn minus rearranging of this, and then there are two terms. These two modulus of these sum of these two terms are the sum of the individuals terms. So, this is less than or equal to N minus A plus of Bn minus B, and it is given in the previous slides, it is given. We have already find out here, right? So, this will come to epsilon by 2 and epsilon by 2, and this means epsilon. So, the whole here An plus Bn minus A plus B is less than epsilon for every n is greater than M, and henceforth this is the definition of limit of a sequence. So, this sequence An plus Bn is converging or having the limit point as A plus B. Similarly, we can prove An minus Bn. So, in place of addition, you can just replace by subtraction. Let have this in a detail. So, for any arbitrary epsilon is greater than 0, there exist two numbers, two natural numbers M1 and M2 such that An minus A is less than epsilon by 2 for n is greater than or equal to M1 and Bn is greater than or equal to M2, right. Bn minus B is modulus is less than epsilon by 2 for every n is greater than or equal to M2. These are by definition itself, by definition of limit An equal to A and limit Bn equal to B, right. Now, taking this maximum of these two natural numbers M1 and M2 and name it as M. So, M as a maximum of M1, M2. We can have the same relationship, but here we have replaces M1 as M. So, N modulus of N minus A mod less than epsilon by 2 for every n is greater than or equal to M, and Bn minus B modulus is less than epsilon by 2 for every n is greater than or equal to M. Now, use these two, calculate this one here. So, this is the nth term of the sequence N minus Bn, and this is the limit of this one A minus B. So, the difference between I have taken here something like An minus L, right, and this is L. So, N minus A minus of Bn minus B, I can write this one, and then these two, the difference of these two terms is always less than or equal to the sum of the individual terms. So, N minus A modulus plus of Bn minus B modulus, and this will comes out to be epsilon by 2, this is epsilon for every n is greater than or equal to M, and henceforth the limiting value of that sequence is N minus Bn is nothing but A minus B. We have already proved. The third one, that is product of the two sequences, has the limit value as the product of the limiting values, are quite tricky. So, you have to be very careful when you are going to prove this theorem. So, for that product, firstly you must remember the theorem of convergent sequence which are bounded. Every convergent sequence are bounded, and by the condition itself it is already given that limit An converges to A and limit sequence Bn converges to B, right. Similarly, so that means this sequence An is a converging sequence, and henceforth it must be bounded. It must be bounded, and once it is bounded, then I am going to use the second definition of boundedness, that is any sequence An is bounded if there exists a real number k such that each term modulus of each term of the sequence is less than capital K, right? So here, so since every convergence sequence is a bounded sequence and n is a converging sequence, therefore there exists a positive number, positive real number such k such that n modulus is less than k for every natural number n, since n is a convergence sequence. Now I am going to calculate an bn minus ab modulus of this. So for this I am adding and subtracting the same number, same term an into b, n into b. So once I subtract here and once I add here, there is no, there is no deflection at all. So and now rearranging these terms. So taking common from an in these two terms. So bn minus b, an into bn minus b, and taking b common with these two terms. So this will comes out bn into an minus a, right? Now an, since these are all are in the modulus, so the individual modulus is less than or equal to that one, greater than or equal to that one. So I can write this one, the whole an bn minus ab modulus is less than modulus an into modulus bn minus b plus modulus b and modulus an minus a. We know this that this is less than epsilon by 2, right? And this is also less than epsilon by 2 for every n is greater than m, right? We already know this one. So I am going to use this one. Since this each term of n as a converging sequence, each term of n, we have already shown that there exists a real number k, a small k. Henceforth modulus of n is going to be less than a small this k, bn minus b, and modulus b is bn minus an minus a. Now I am going to use this definition of the limit of the sequences. So for given epsilon is greater than 0, there exist two numbers m1, m2 natural numbers such that n minus a is less than epsilon by 2 divided by modulus b plus 1. And this modifications is coming out due to this one. This is the modulus b. So I have to keep in such a way that the whole things is comes out like less than epsilon. And to rearranging this one, we have modified an minus a and bn minus b in this way. So an minus a modulus is less than epsilon by 2 divided by modulus b plus 1. You can take anything. It doesn't matter at all, because these are the epsilon are arbitrary. So the multiplying or dividing by some constant does not affect anything. And bn minus b taking epsilon by 2 by k. Now you can see here bn minus b, if I take epsilon by 2, this is kk divided by k is cancel out, and this will comes out to be the whole terms, it comes out epsilon by 2. Similarly here, if I take epsilon by 2 divided by modulus b plus 1, the whole term is less than epsilon by 2, and that is what our idea is. That is what our idea is, right? So taking maximum of these two natural numbers m1, m2 and renaming it as m, we have an minus a modulus is less than epsilon by 2 divided by modulus b plus 1 for every n is greater than or equal to m. Similarly, bn minus b modulus is less than epsilon by 2 divided by k for each n is greater than or equal to m. Now go with the calculations. An bn minus ab modulus, right? And this has been comes out at this place, k into bn minus b modulus plus modulus b into an minus a modulus. I am going to use the same things. So an bn minus ab has been comes out that this is less than or equal to k into bn minus b plus modulus b an minus a modulus. Bn minus b is already given here. It's already given epsilon by 2 by k. Putting this value here, this will comes out to be cancel out of this k, right? So this is k into this. So this will comes out. This is cancel out here. Similarly, modulus b is an minus a. Put this value. So this will comes out modulus b epsilon by 2 divided by modulus b plus 1. So here you will see epsilon by 2 and here you will see less than epsilon by 2. This will makes you the whole terms is less than epsilon, and that is the definition of limit. That means the sequence a in Bn has the limit as ab. Now I think I will explore much more for your clarity. So a and bn minus ab, we have already calculated k into bn minus b modulus plus modulus b into an minus a modulus. Now I have chosen this epsilon, or using the definition of limit of sequence an or bn in such a way that it's going to be epsilon by 2 epsilon by 2. So for this bn minus b, I have just chosen such that bn minus b modulus is less than epsilon by 2, and since k is above, so divided by k, that's all, right? And k is a positive number, so you can write this one as epsilon by 2 into k, and this will comes take this out. So this one is comes out k into epsilon by 2 into k cancel out, plus modulus of b into epsilon by 2 divided by modulus b plus 1. So modulus b divided by modulus b plus 1 is always less than modulus b is a positive number. So modulus b plus or modulus b plus 1 is always less than 1, right? So that means this an bn minus ab modulus is going to be less than, strictly less than epsilon by 2 plus epsilon by 2, and this is epsilon, and for this happen for every n greater than or equal to m. So this is the proof. There is no need to remember anything. It has very clear proof and a very easy proof to you. Now we are going to prove the last one, the fourth one, and that means the quotient of limit of quotient of two sequences a and bn is equal to the quotient of limiting value a in ab, right? So limit n tends to infinity a and bn is equal to individual limit n tends to infinity a n divided by limit n tends to infinity bn, and that's equal to a divided by b, right? Where each denominator, whatever the denominator we are using, is not going to be 0 for each n. That means for any natural number, each term of that sequence bn is not going to be 0. So it's a non-zero sequence, right? So how to show this? So firstly we show that if limit bn is equal to b is not equal to 0, as we have already assumed here, then there exists a natural number m1 such that modulus of bn is greater than 1 beta 2 modulus b. This is quite a big claim. So for this claim we have to show that individually that it really happened, right? So consider on sequence bn. So since limit n tends to infinity bn equal to b, therefore by definition of limit we have for epsilon equal to 1 beta 2 modulus b. So the trick is here, the trick is to take epsilon a particular value, that is 1 by modulus b, not 1 by 2, but you can take 1 by 3, 1 by 4, 1 by 5, whatever you want, but modulus b must be there, so that I can prove here, since I have taken bn, modulus of bn is greater than 1 by 2 modulus b, therefore I have just chosen epsilon as 1 by 2 modulus b. So for a natural number m1, n is greater than or equal to m1, now we calculate bn minus b modulus. And since bn is a converging sequence, or having the limit point as b, therefore modulus bn minus b modulus is less than epsilon by definition, and this epsilon is nothing but half of modulus b. So now modulus bn minus b can be written as modulus b minus of modulus bn, right? Is it okay, right? I think it is okay. So this is less than or equal to modulus bn minus b. Obviously the difference of individual modulus is always less than modulus of the difference of that individuals, right? So this is less than or equal to epsilon, this is epsilon. So this is given. Now rearranging the whole things. So take this this side. So b minus of half b1, and take this side here. So this is less than modulus of Bn. Now this is going to be half of modulus B. So modulus Bn is always greater than half of modulus B, and this is happens only for n is greater than or equal to m1. Remember this one. So what is the trick here? The trick was the difference between two numbers is always greater than or equal to the modulus difference of the modulus of these numbers. This is the trick. This was the trick. This was the only trick here we have used, right? This is the only trick. And this one Bn minus B is less than epsilon. So by these two you will reach at the conclusion that this Bn is always modulus of Bn is always greater than half of modulus B, and this is only possible for n is greater than m1, right? So now calculate a and Bn minus a by B. So rearranging this one, taking this one as LCM, so B into Bn, and this B is here, so B into B, An minus A into Bn, and rearranging these whole terms. So Bn minus AB, so what we are doing, we are adding AB and subtracting AB here. So here it's a subtraction and here it's a addition. So here it's a subtraction and here it's addition, right? So B and rearranging the terms, so B into An minus A minus A into Bn minus B divided by B into Bn. So and the whole terms, this whole terms taking the individual modulus, it will less than or equal to that. So this is less than or equal to modulus B, modulus of An minus A plus modulus of A, modulus of Bn minus B divided by modulus of B, modulus of Bn. So taking modulus individually, this will comes out to like this. And doing the same thing, since the modulus of Bn we have already written here, modulus of Bn is always greater than half of modulus B. That means the whole quantity is less than or equal to of this quantity. So 2 by modulus of B, right here, An minus A plus of 2 into modulus of A divided by modulus of B ka whole square, so B and B square. Here B and B is cancelled out, Bn minus B modulus, and this is greater than or equal to, this is for each n is greater than or equal to m1. Now use the limit point of the sequence of n. So limit n tends to infinity n equal to A and limit n tends to infinity Bn equal to B. Therefore using the definition of limit, and for a given epsilon greater than 0, there exist m2 and m3 natural numbers such that n minus A is less than 1 beta 4 modulus B epsilon. Look at the structure of this. We are trying to find out this difference as less than epsilon, right? That's why we have taken this structure, and this is this is true, or this is hold for each n is greater than or equal to m2. Similarly, Bn minus B modulus is less than 1 beta 4 modulus B ka whole square epsilon divided by modulus A plus 1 for each n is greater than or equal to m3. And taking this maximum of these three natural numbers m1, m2, m3, we have An minus B, An divided by Bn minus A by B modulus is less than epsilon by 2 plus epsilon by 2, that means epsilon. And that is the proof of our theorem. So we have already proved these four theorems. You just go through it and remember the definition of limit of sequences. You will easily prove analytically. So for this lecture, it will be the end of this lecture here. Thank you everyone.